let's get it going from the current slide, which is actually going to be in 4.8, but we have that one last example to do in 4.7. So as soon as that comes up, we'll do that. Let me go over the announcements. There are a bunch of them, but I'll try to make them quickly. Yes?
I thought you said we were skipping 4.8.
What's that?
I thought you said we weren't doing 4.8.
No, we are doing 4.8, yeah. 4.7 and 4.8. But I said last time, remind me to go to 4.8 and not to go to 4.7 because the slide isn't in there. The last example is in there. Okay. I think I've checked before, and none of you are graduating this term. But if you know of someone who is, and they may be out of time, but the deadline for the scholarship opportunity at UAB and University of Alabama at Tuscaloosa is today. So if you know of anyone, and if it started on, they got to get it done really soon. Now, the other thing was this NASA Community College Aerospace Studies Program, okay, NCAS. I announced this to you last time, didn't I? Okay. I won't go over that again. However, the deadline for that is, the online session for this, information session for this, is today, 5 to 6 this evening. This is Central Time, I'm almost certain. 5 to 6, and these are all times of Central Time, okay? So that's the information session, and the deadline is due March 5th, which is Monday. So get hopping on that if you're interested in it. I've got all the information here if you want to see it. Okay? Another thing, this is Quality Education for Minorities, a program that works closely with National Science Foundation, and they have extended this Talent Development and Innovation in Sciences Summer Internship Program. They extended the application until tomorrow. Okay, so this has to be in by tomorrow. This TDIS, Talent Development and Innovation in Sciences Summer Internship Program, 10 weeks paid internship, including housing. You don't have to provide your own housing in the Washington, D.C. area, and conducting research projects for National Science Foundation. And they also will assist you in the next school year to attend conferences, workshops, trainings, so you can get financial assistance for that as well. So if you want more information about that, there it is. Deadline is tomorrow. Okay, this is a company, I think, looking for employees. It's called First Call Quality Services. They're out of Indianapolis, Indiana, but they're going to be at the One-Stop Center right over here at the Millsap building Tuesday, March 6th. Okay, they're taking applications for the job fair, and they're looking for two different things: quality inspectors paying $11 an hour, or team leaders paying $13.50 an hour. Tuesday, March 6th, they'll be at the One-Stop Career Center from 9 in the morning until 1 in the afternoon. Benefits are available. It's not just an hourly wage. They do provide benefits. Applications must have a clear background check, not a Jared Kushner. I didn't say that. Okay. Driver's license, high school diploma or GED, and this is the little bit of a kicker, automotive manufacturing experience preferred. Not required, but preferred. And if you have more questions, Ms. Brenda Thomas or Dorothy Henry over in the One Stop Center can answer those. They will be there 9 to 1 on Tuesday next week. Okay, math team is always looking for participants, and that's Mr. Rossi usually meets with them on Fridays at noon, but not this Friday, okay, because we'll be in a meeting in Jasper, okay? And they meet every Monday afternoon at 3 in the Birmingham West Campus, the Science Building, which is the C Hall, and in C100. They're on the first floor. any of you want to do practices on this campus, I'll be glad to try to work it in during my office hours. And I've told you before about tutoring, where you can either receive tutoring, or I think you guys can do tutoring because y'all are advanced enough that you should do it quite well. That one's already finished. And normally after this class is over on Tuesday and Thursday, I'm in my office for the rest of the afternoon until 5:15 usually. Not today, okay? Today, I've been instructed as soon as I'm through with class, go and grab my lunch and eat lunch, and then go over to the Ethel Hall conference room and meet with the dean, and we're going to be working on fall schedule. Well, there's a lot of changes happening in that, okay? And then that's going to go up until 2. Then we have a meeting that's going 2 to 5, okay? Except I can't even stay till 5 because I have to go up to Jasper for a sort of like a pre-meeting this evening. I have to be there between 5:30 and 6. So I'm going to have to leave here by 4 to get up there. So actually, once I eat lunch, then I'm going to drive the car over there, even though I don't need to have it there. But that way, then when I leave that meeting at 4, I just don't hit the road. I'm not coming back to my office. If I remember to get everything together, that's what I'm going to do right after lunch. So basically, almost no office hours a day. I'll be in my office eating lunch, so you can see me then. But after that, I'll be Ethel Hall and on the road. So, just to let you know. And then Friday, tomorrow, not on either campus. I'm going to be at Jasper. Okay. And then again, none of you are graduating this term, but if you know anyone who is, they're having graduation meetings coming up next week, Monday, Tuesday, and Wednesday. Monday's on the Birmingham West Campus in the ACAT building, 6 o'clock in the evening. Then Tuesday, they're here on this campus in Ethel Hall Auditorium. Then on Wednesday, they're back on Birmingham campus, 1:30 for both Tuesday and Wednesday, 1:30 here, 1:30 there, again in the ACAT building on Birmingham West campus. So, any questions on any of that kind of stuff or on trig stuff? Okay? Oh, wait, let me mark Sydney here. Okay. Oh, man. I'm so out of energy. We're in Chapter 4, Trigonometry, and we're going to start our last section in this. 4.8 is Applications and Models, okay? So what we're going to do first is do example 7, the last section, the last example in section 4.7. And then, in fact, we did 7A. We didn't have a chance to do 7B. So we're just going to do 7B, and then we're going to start in 4.8. So since, I think this looks like probably the best slide to use, so let's just do 7B from 4.7 here, unless there are other questions. Are there? Okay. Write an algebraic expression that is equivalent to each of these expressions. And here is the expression in question now. Okay? The cotangent of the arc cosine of 3x. Okay? I don't know if you remember the A part that we did. We're going to do this one somewhat similar to it. How would you begin? Second? Okay. Well, before I rewrite it, I would set it to something. What do you want to set it to? Theta, our favorite. Okay. Set it equal to theta. Now rewrite that. What would that imply? That cosine of theta is equal to 3x. Okay? Now, this is where I draw my picture. I draw ugly pictures. They're not very attractive at all. And okay, so what I'm going to do is draw a unit circle. Okay. I don't draw circles very well at all. Ooh, that's really starting badly. Okay, that's not a very good circle, but just imagine it is. Okay? Now, here's sort of a little problem here. We have a variable x. So what I'm going to do is call this horizontal and this vertical. Okay? Just to keep from confusing the x's and call it xy, because we already got the 3x in the problem. Okay? And that's going to be a unit circle on the horizontal vertical axis here. Okay? Not xy axis, horizontal vertical. Okay? Now, it says cosine of 3x. And here's why I chose to use a unit circle, because I'm going to write that as 3x over 1. Okay, that's what made it a unit circle. The radius is 1. Now, what is the cosine of some angle theta? What would be its value? Call another hen. Adjacent over hypotenuse. And the hypotenuse is 1, so the adjacent is 3x. So there's going to be, let's call it 1x, 2x, 3x. We don't know what x is. We know it has to be something less than 1/3. Okay? So I've drawn it in that way. They give that as part of the problem. I didn't write that down. I probably should have. 0 is less than or equal to x is less than 1/3. And the reason for that is you can't take the cosine. The arc cosine has to be between -1 and 1. We're not even going to let it be negative. We're going to let it be positive. So it's between 0 and 1. Well, 3x is between 0 and 1. That means that x is between 0 and 1/3. Okay? So that's where that comes from. Okay? So I'll draw my little x's there to be less than 1/3. Okay? So that's going to be my y, my adjacent side is right there, 3x. Okay? And we know the hypotenuse here is going to be 1. Okay? So this is 3x over 1. That's your cosine. All right. Now, that makes this that angle theta that Sarah made up. Okay? The angle theta. What we're asking for is what is the cotangent of that angle theta. And what is cotangent, by the way? It's what? That's it, adjacent over opposite. So your adjacent, we know what that is. That is 3x. And what is the opposite here? Say again? Oh, and we can't figure it out either, can we? Of course we can. Square root of 1 minus 9x squared. You got it. You knew that right off the top. There is, this is that expression right there in terms of x. 3x over the square root of 1 minus 9x squared. Good deal. They have a checkpoint there, which is another type problem. I would highly recommend you do it. On the checkpoints, your audio-video solutions are at larsonprecalculus.com. All right, let's do the vocabulary on 4.7 exercise. Okay, we have sort of the table here for the first 3. They give you 2 pieces of information. You fill in the rest of it. Do all of you have your books? You do, don't you? Okay. So this is the top of page 324. Number 1, they tell you y is equal to the arc sine of x. So what the first thing is, what's an alternative notation? In other words, an equivalent equation.
The sine with the -1 x.
Okay, wait just a second. Oh yeah, okay. Arc sine and sine to the -1 mean the same thing. So that's not, it means write the equivalent equation to that where you're not using an inverse or arc? What would that be? Sin y is equal to x. That's the equivalent or alternative notation. Now, remember, the last piece of information that tell you that the range of that first function, y is equal to arc sine x, the range being the y values they could take on, would be between minus pi halves and pi halves. What would be the domain? Negative 1 to 1, including, so those are equal signs, is less than or equal to on both of those. All right, number 1 went well. Let's look at number 2. Here, the alternative notation is y is equal to inverse cosine of x. What would be the function? That's say again? Cosine y is equal to x. Perfect. Here, the domain is minus 1 to 1, including the endpoints. What would be the range on that one? 0 to pi, exactly. Cosine to be 1 to 1 has to go 0 to pi. Perfect. Number 3, the function is y is equal to arc tangent of x or inverse tangent of x. What would be the alternative notation? The equivalent equation. So tangent y is equal to x? Perfect. Okay. What's the domain of that one? Of the values for x? I like to think of it as the second way you said it. Tangent y is equal to x. What values would x take on that? All real numbers. Only since it's x, it would be this way. Okay. And what would be the range? See, this one has 3 points. In other words, what are the y values? And remember, you could say that as x is equal to tangent y. Yep. Basically, look your 2 lines above. It's going to be almost like that. There's 2 things you leave out. The equal sign. It's negative pi halves less than y less than pi halves. Because tangent is not defined at half pi's. Not defined at all. So they'll be like this now. Going from minus pi halves to pi halves. Those are horizontal asymptotes they cannot ever reach. Number 4. A trigonometric function has an blank function only when its domain is restricted. Inverse. Okay, the and help there. Okay. Homework exercises here would be any of the odds, 5 through 17. Those are all at Calc Chat, 5's at Calc View. Do number 19. Sorry. I'm having trouble breathing. I should have gone down to the office in between classes. I usually do that, but I didn't this time. Do 19 is a Calc Chat. It's not a Calc View. Do any of the odds 21 to 35. They're all at Calc Chat. 21's at Calc View. Do 37 is a Calc Chat, not a Calc View. Then do any of the odds 39 to 43. They're all at Calc Chat. 39's at Calc View. Do any of the odds 45 to 49. They're all at Calc Chat. 45's at Calc View. Do any of the odds 51 to 61. They're all at Calc Chat. 55's at Calc View. Do any of the odds 63 to 71. They're all at Calc Chat. 65's at Calc View. Do number 73. It's the only one like that. It's at Calc Chat, not at Calc View. Then do either 75 or 77. They're both at Calc Chat. 75's at Calc View. Do any of the odds 79 to 83. They're all at Calc Chat. 83's at Calc View. Do any of the odds 85 to 89. They're at Calc Chat. None of them are at Calc View. Do 91, only one like that is a calc chat, not a calc view. Then do any of the odds 93 through 97. They're all at calc chat, none of them are calc view. And then on the application problems, do any of the odds 99 through 105. And they should all be at calc chat, not at calc view. Exploration, there's 3 true false. 107 is the one whose answer is given. So I would do that and think through that. Then I said before, we don't usually mess with inverse secants or cosecants because they're fairly messy. 111 and 113 are asking you to think about those. So if that gets too messy for you or too esoteric, don't worry about it. Okay? Now, evaluating inverse functions, we did do something like that. Do any of the odds 115 to 119. They're all at calc chat, not at calc view. And then do any of the odds 121 to 125. They're all at calc chat, not at calc view. And then there's, one more. Goodness gracious. End of the week, I'm running out of steam. 127 is a good problem. Maybe a little more involved, but see if you can work through that. It should be at calc chat. There's a think about it at 129, and you can think about it if you'd like. And that's it. So we're ready for 4.8, which is applications and models. Now, this is the last section of the chapter, which means it's the last section for your second test. Second test, remember your first test was 4.1 to 4.4. The second test is 4.5 to 4.8. A lot of graphing on that one, on the one coming up. But one reason I'm mentioning it now is I need the first test to be coming in. I don't like you to be 2 tests behind, so try to get your first test in. If you can wrap it up this weekend, that would be a very good idea. Okay? And that way, next week, probably sometime next week, we'll be ready for the second test. Okay? So, let's look at 4.8, applications and models. Here are the objectives. We're going to solve some real-life problems, kind of real-life problems, involving right triangles. Remember, trigonometry is the study of triangles. We'll solve some real-life problems involving directional bearings. The used trig, they kind of set themselves up a little bit differently, but it all still works. And we'll solve some real-life problems involving harmonic motion. That's also called periodic motion. So let's look at applications involving right triangles. In this section, the 3 angles of a right triangle, rather than Sarah's favorite theta, we'll be using capital letters A, B, and C for the angles, where C is always going to be the right angle, the big angle. One reason they do this is then the lengths of the sides opposite those angles will be the letters small, lowercase a, b, and c. And c, then, of course, since it's opposite the big angle, it's going to be the hypotenuse. And good old Pythagorean theorem usually is written as a squared plus b squared equals c squared. Yes, so that fits nicely with what our convention is. Okay? So, they skip example 1. Shame on them. Okay, let's do example 1. And by the way, example 1, it says see larsonprecalculus.com for an interactive version of this type of example. Goodness, I'm running out of energy. I feel like I just have been run over by a truck. I don't know what that feels like because I never have been, thank goodness. But anyway, it says solve the right triangle shown at the right for all the unknown sides and angle. So I'll try to draw this on the right also. And I'll put that's supposed to be a horizontal line there. an angle going up to here, and a vertical line there. Okay, just imagine that's the right triangle. Use your imagination. Ooh, that's ugly too. That is your right angle. So therefore, we're going to name this one C, capital C. It doesn't matter what you name the others. They make this one A and this one B. Okay? Which, of course, would make this side over here opposite A, opposite B, little b, and opposite C, little c, which will be your hypotenuse, which is what the convention is. Now, we know from this symbol here that C is equal to 90 degrees. Okay, we know that. That's the right angle. Okay. The other things they give you in this triangle is the angle A is equal to 34.2 degrees. That's a 4 there, not a 9. Okay? And they give you that B is equal to 19.4. Now, what we mean to solve the triangle is find everything we don't know. Well, we know three things here. What we don't know is little a, capital B, and little c. And why don't y'all work on that? And I'm going to run down to the office and get something to drink first. Not learning how to sing. I'll be right back. Sorry about this. I hate doing this. Maybe I should leave it right away. I get more to it. Did you understand what's happening here? Oh, man. Okay. Now, anyone got a solution yet? What did you go for first? What's that? Capital B is a good thing to go for first. How do you get that? Okay. So you add 34.2 to 90, and that gives you 124.2. And do what? From 180. And that would give you 55.8 degrees. Everybody get that? Excellent. All right. How in the world are we going to get little a and little c? With what? Okay. Take a function, though. And here's what you ask yourself. What trig, which one do you want to go for first, by the way? Little a? Okay. Which trig function is going to relate what you know? Now, here's a little thing I do. I leave it as a possibility I may have made an error here. So I want to use only the things they give me unless I can't possibly not, okay? So I want to use the angle A, the side B, and you want to do A first. So what trig function relates angle A to sides A and B? The tangent does. And how does that read? The tangent of 34.2 degrees is equal to A over 19.4. I don't think they gave any units there, did they? No, just number. Okay, how in the world do you figure out what A is? Multiply both sides of the equation by 19.4. And that wipes out that, and that gives you A is equal to, and you might need to use your little old handy-dandy calculators. And what do you get? A little louder? 13 point what? Okay, let's round that to 2. Now, the only reason I do that is because you see you have 3 significant digits here, 3 there. Okay? So I don't see any way that we can justify getting more than 3 digits there. Okay? So A is going to be 13.2. Now, time out. Let's ask ourselves if that makes sense. Okay? Now, here's something about triangles. The largest angle in the triangle is always opposite the largest side. Okay, now this is in any triangle. The largest angle is always opposite the largest side. Meaning that the smallest angle is opposite the smallest side. And the middle angle is opposite the middle side. It's sort of like Goldilocks. Okay? Now, does that sort of make sense? This would indicate, since we're given this is 34.2, we calculated it with 55.8 degrees, then we figure this side should be larger than that one. Ding, 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 it is. Okay? One more thing to do. What is that? Find C. How do we find C? There's actually multiple ways. Say again? I can't. Oh, okay. There are multiple ways, okay? And what would be one of the ways? Pythagorean theorem certainly would give it to us now that we know this. But of course, this is also a calculated value rather than the original. But let's do it. 19.4 squared plus 13.2 squared should equal what? C squared. Okay? So let's see what that is. Y'all got your handy-dandy calculators. So C squared should equal 19.4 squared plus 13.2 squared, and that should be, anyone got that punched in yet? You took a square root too? Okay. So you got C is equal to 23.5? 23.5. Now, On the surface, that looks reasonable too, because C should be larger than either A or B, and it is. Okay? So that makes me feel warm and fuzzy. I still don't know for sure if it's right. Let's do it the other way, using the stuff they gave us. And what would that be? Is what? Angle A and side B. Is there any way to get C out of that? How? Cosine of this should be, adjacent over hypotenuse. So let's do that and see what we get. This is just a way of checking. The cosine of 34.2 degrees should equal 19.4 over C. Okay? That's pretty ugly writing. So let's multiply C by both sides to get rid of the C there. I don't like it in that denominator. And then also divide both sides by cosine of 34.2 degrees. So divide that by cosine of 34.2 degrees. Okay. Now, that goes out here, so that leaves you C is equal to, I know this is messy here, it's 19.4 divided by cosine of 34.2. This thing right here. What would that give us? 23.5. All right, we've confirmed that should be your answer. Most of the time you'll come out within either exactly on or within like one decimal place. So 23.5. Yes, I feel really warm and fuzzy about it now. So I think we got it right. Let's see what they got in the book. Angle 55.8. Yes. Okay. Where is it? Where is the second one? Let's see. Okay, A is 19.4. No, B is 19.4. What? No. Oh, okay. Times tangent. Got it. Okay. Okay, 13.2. Yep, that's what gave us our A. And then the C would be, and they did it the second way. They didn't use Pythagorean theorem, 23.5. Okay. I was thinking the red answers were their answers and that they're givens. Okay. Sorry about that. There is a checkpoint there. Well worth your time to do the checkpoints. All right, let's move on to example 2, which is in the text. Only it's not the same problem, is it? Okay. Do you want to do both of these or just the one in the book? Or just the one on the slide? Both of them. So let's do this one first, example 2, which is on the slide set, but it's not in the book. Safety regulation states the maximum angle of elevation for a rescue ladder is 72 degrees. And that's pretty steep, folks, if you've ever been on ladders. That's a pretty steep thing. Fire department's longest ladder is 110 feet. What is the maximum safe rescue height from the information they gave us? So what would you do first? Draw a picture, always, okay, or most of the time anyway. All right, so here we're going to have a building there. Okay, we don't know how tall the building is or anything. But, and let's just assume that it's on level ground. Most are. And let's say that this is our, I don't know if that's 72 degrees. Let's just imagine it is. I just made up something there. And the longest ladder is 110 feet. Okay? The question is, what's the maximum height? Safe rescue height. That would be this. Okay? That's what we're looking for. This is the unknown. Pictures are worth thousands of words. Okay? So, how would you approach it?
Or the opposite of your hypotenuse.
Okay, very good, because we're relating the angle with the opposite side and the hypotenuse. So what trig function is going to do that relation? Sine. So the sine of 72 degrees, it needs to be what? H over 110 feet. Okay? And what would you do? Solve for H. That's what we're looking for. What would you do? Say again? Multiply both sides by 110 feet. Okay? That gets out of the denominator, which was messy there, and gets over here. Okay? Which is what we need. And so H then would be, goodness gracious, 110 times sine of 72. Be sure you're in degree mode, but folks. What do you get? 104.6. A little louder? 104.6 feet. Okay? Now, it's probably what the book gives too, but again, I'll look at this. At best, 3 significant digits. Only 2 here. So 2 significant digits there would be 100 feet. Okay? And if I'm walking up a ladder at 72 degrees, I think I want to give myself that cushion. Okay? I would not round this up at all to 105. That's beyond the safety limit. So on a problem like this, I tend always to round down. So I would say either 104 feet or even safer, just over 100 feet. You know, now, that would give you the maximum safe height. You know, if I were really working in the fire department and stuff, I would want to know what's the maximum distance I should be, the minimum distance I can have to the building before it's not safe anymore. Then I'd use the cosine, you know, and then I make sure I don't get any closer than that, because any closer than that, you're going to be steeper than 72. Because that to me would make more sense. How far from the building do I need to put the base of the ladder? Who knows how high that's going to be? So I would have phrased the problem probably a little bit differently. But if someone's up there, they probably want to say, "Can you get me?" And they'll say, "Yeah, I think we can." You know. All right. So, but you see, there's lots of ways, lots of problems you could get out of that same setup. So here's the deal. There's their picture. Okay. Boy, this is a tall building. Okay. And they sketch it this way. I wasn't about to draw the ladder truck and that kind of stuff. But you see everything else is pretty much like we did. 110 times sine of 72, which is 104.6. Exactly what you said. But I would have rounded that down somewhat. I would have said no more than 104, okay? And that's above the height of the fire truck. So if the fire truck is sitting up, you know, you might be able to get a few more feet out of it. Okay. That was example 2 in the slideshow. Let's do example 2 from the text. The height of a mountain is 5,000 feet, okay? Let me find which. Oh, okay, that's the short mountain. Okay. So here's an ugly little picture. Okay, and this is 5,000 feet. Okay. The distance between its peak and that of an adjacent mountain is 2,500 feet. That's too regular. Okay. So this is from here to here is 2,500 feet. Now, obviously, mine isn't drawn to scale, because that should be 5 times, no, half as far. Whoa. No, 25,000 feet. Okay. 10 times, no, 5 times as far. That's what I thought. Okay. Mine isn't. Okay. The angle of elevation between the two peaks, so you're standing on this peak, looking up at that peak, this is your angle of elevation. What you want to name it? Well, they tell you what it is. It's 27 degrees. Now, again, mine isn't drawn to scale anywhere close. In fact, I don't think theirs is drawn to scale very well either, because, no. I'm sorry, I misinterpreted, because I was thinking something easy to measure. They are saying something entirely different. Because to me, you could measure, at least on a map, the distance between the two peaks. They're saying this is, they're meaning the actual distance between the peaks. Who knows or cares what that is? Because that's as the crow flies. I mean, you can't walk there. You can't string a string between them. Maybe you could, but I wouldn't want to. But this is a real life problem. Is it? Okay. All right. The distance between those two peaks, as the crow flies, is 2,500 feet. Crows care about it. Okay. The angle of elevation between the two peaks is 27 degrees. What is the height of the adjacent mountain? With the adjacent mountain being larger. So what we're looking for is this height here. Let's call that H here. How are we going to do that? This might be a little hint here. There's your right angle. We're assuming that you're measuring everything from equal elevations and that this is going straight up, that's going straight up. So, yeah. Ha! Okay. Find this portion and then add 5,000 to it. Right? So how do we find this portion? How do we find that portion? Sine. Perfect. The sine of 27 degrees is equal to okay. You want to call that, what did you? A. Why not A? Because we already used H. So it would be A over, they usually use A for adjacent, but that's okay. You can use it any way you want to, over the hypotenuse, which is 25,000. Okay, and A is going to be in feet. How do we solve that? Multiply both sides by 25,000. Right? These go out, and your A is equal to, someone figured that out yet? Anybody? 7,300 and what? Huh? 11,000. I can't hear well. I was going to say that sounded a little small, but let's see. 11,000 what? 49. Okay, let's not do any more. Okay. And then we're going to add to that. Whoa. Obviously, their picture isn't the scale either. Because we're going. That's before you added the 5,000, right? Or did you already add the 5,000? Okay, then you add 5,000. And that gives you 16,349 feet. Okay? They rounded 350. First time they've done something like that right, 16,350. Though they have 4 significant digits, and really we only have room for, I think, 2. You might even say the 5,000 would only be 1, but yeah, that's close enough. Okay. Oh, goodness gracious, I'm so out of energy. All right, any questions on that? Okay. That's the building again. All right, they're skipping example 3 as well. So let's go back and do example 3. Goodness, I haven't felt this worthless since my first round of treatment, and I haven't had a heart in 2 weeks now, so not quite 2 weeks, close to it. I don't know why.
Maybe your white cell thing's
What's that?
Is your white blood cell thing still low?
Yeah, everything's down. So, yeah, that's why I'm feeling tired, but I should be bounding back, and I don't feel like I'm rebounding well at all. I feel like silly putty throwing through the wall. Just hangs there. No rebound. Okay, let's do example 3. Fairly similar to the one we just did. A little bit different, though. At a point 200 feet from the base of a building. Okay? They drew the building on this side now. And again, we're going to assume that we're level territory here. And here is the base of a building, and there's the building there. It should have a horizontal roof, but it doesn't look like it. Okay. And here's the point somewhere out here, we'll say right there. This is the point 200 feet from the base of the building. Okay? The angle of elevation to the bottom of a smokestack, and the smokestack is on top of the building. Okay? So the angle of elevation to the bottom of the smokestack is 35 degrees. Mine isn't to scale. Okay? Whereas the angle of elevation to the top is 53 degrees. Okay? Okay, let me clean this up a little bit because I was pretty sloppy on that one. Oh, man. Okay. There's the 35 degrees. There's the 53 degrees. Find the height S of the smokestack alone. So this is what we're looking for. S, the height of the smokestack alone. All right. Now, here's the assumption everywhere is that that's your right angle. The building is perpendicular to the ground, which at least near the building it usually is. Okay, most of the time it is. How are we going to figure the height of the smokestack? Okay, using the right. Okay, using the 35, we'll find the height of the building. Using the 53, we'll get the whole height from the base of the building to the top of the smokestack, right? And then subtract and you get the height of the smokestack. So how do we do that? What we know is your point from which you're taking your measurements at 200 feet from the building. So how do we do this? Yes, tangent is the angle that we use. All right, so let's write me a couple of equations then. Do you want to give this a name? You want to name that B maybe for building? Okay, and then the big height here will be S plus B. Is that okay? All right. Let's use those names to do our calculations. And I heard someone say tangent is the, Jared said tangent is the trig function we're going to be using. So you tell me what to write down with tangent. Help me. Okay. Tangent of 35 degrees. Okay, what is tangent again? Taking opposite away. Yeah, opposite over adjacent. B over 200. Everybody see that? Opposite over adjacent. Okay, so we can figure out how tall the building is by multiplying 200 by both sides. Okay, that gets rid of the 200 there, so B is equal to 200 times the tangent of 35. Anyone get an answer for that yet? Say again? 140 what? 140? Okay. 140 feet, I believe it was, yeah. So the building is 140 feet tall. Next. Okay. S plus B is going to be, well, wait, let's not do that. Let's take it one bite at a time. Okay. Say again. Tangent of 53 degrees is going to be the S plus B over 200 feet. Okay, and what will you do first? Multiply by 200 feet. So that goes out, and multiply this side by 200 feet. And 200 times tangent of 53 is approximately 265. Okay, let's just round it. 265. Is that what you said? Okay, I can't. My hearing's bad, so. Okay, 265 feet. And that's S plus B. So to get what S is, you subtract the 2, as you said. S is equal to S plus B minus B, which is going to be 265 feet minus 140 feet. And that would be 125 feet. They said 125.4. I really don't think you have enough precision to have the extra thing, because what you're given is at best 3 significant digits. You could argue that's only 1. This is 2, that's 2. How in the world can we even get 3 out of it? I don't think we can, but we'll round to the nearest foot. But you sure can't get to the nearest tenth of the foot from a physics viewpoint. Okay. This is math, not physics, but usually we want our answers to make sense. All right, 125 feet, approximately. All right, let's see if they have an example 3. Wait, that was example 3. Nope, they don't have example 4 either. So let me clear this. Y'all got it? Okay. Oh, man. I'm so sorry, folks. I just feel worthless. Here we have a swimming pool, 20 meters long and 12 meters wide. Now, they just show 2-dimensional. I'm going to try to make it 3-dimensional. I'll probably do a really lousy job of it. I am doing a lousy job of it. Yeah, really bad. Let me see if I can clean those up a little bit. Okay. Maybe I shouldn't try to do 3-dimensional. Okay. That's the surface of the pool. This is 20 meters long, 12 meters wide. The bottom of the pool is slanted so that the water depth is 1.3 meters at the shallow end. So this is 1.3 meters. Now, obviously, mine is not being drawn to scale, okay? Nowhere close to it, okay? And 4 meters deep at the deep end. Okay, I'll hope that's about right. So we'll call this 4 meters deep here. Now you can do that here too and there too. You know, you don't have to have the 3 dimensions. They just show 2. Okay? So that's what they gave us in the problem. Find the angle of depression in degrees of the bottom of the pool. What they mean by that is taking this as your horizontal. What is the angle here? What do you want to name it? Anyone have a favorite? Okay, we can call it capital A. That's fine too. Okay? For angle maybe or something. Okay? Why not? I was thinking theta was going to pop up again. But whatever. Okay. Now, how in the world do we manage to get that angle? Angle of depression. Now, I'm going to do one thing here. I'm going to carry this line all the way over here and indicate this is 1.3 meters here, and the total depth is 4 meters there. I don't know if that helps any or not. Second? Okay, good first step. Subtract 1.3 from 4, and that would give 2.7 meters. So that's this height, the 2.7 meters. Okay, good. Anything else? I'm sorry? Tangent of A is equal to 2.7 over 20. Got it. Tangent A is equal to 2.7 meters over 20 meters. Okay. Got it. And what would that give you? 2.7 divided by 20. You got it yet? What you get there? Okay. Say 0 point, what? What? Okay. Okay, now, when you're not looking for your answers, I would hang on to as many digits as you can. And then when you go to round off, you don't have as much round off error. So I would leave every digit on the calculator. I only write a few of them down. What would they be? 0135 you said, or something like that? 135. But leave them all there in the calculator. Okay? Well, that gives you the tangent of the angle. I want to know what the angle is. How do we get what the angle is? Say again? Arc tangent. Yes, exactly. Inverse tangent. Okay? So do the inverse tangent of that. It's on your screen. Just do the inverse tangent key, or however your calculator allows you to do that, and see what that gives you. And I think they want it in degrees, don't they? Yeah, in degrees.
7.69.
A is equal to what?
7.69.
7.69 degrees. Okay? Now again, I look at the problem and I see no greater than 2 significant digits. So I think I'd go with 7.7 degrees. Only at the end do you round. 7.7 degrees. Let's see what they got. They got the 7.69 also. Shame on them. Okay. But anyway, that's what you get. Now, where did you use the 12-meter width of the pool? You don't. There's no such law of conservation of all the data given. You don't have to use it if it isn't pertinent. You know, it's extraneous information. Who cares what the width of the pool is? It has nothing to do with the problem. Now, just as a dumb story, when I first started teaching, I was an adjunct Math 090 instructor at Jeff State. And they did lots of little things. And one time, I just remember this so well, one of the problems was a student goes to the grocery store and buys 3 bags of chips. 3, see if I can get it right. No, 3 boxes of cookies. And there are 48 cookies in a box, and 3 boxes of cookies, and he pays, and they're $1.19 a box. How much did he pay for the cookies? Well, it's 3 boxes times $1.19 a box. Okay, so $3.57 or whatever it is. I had some students that had it up into 80 or 90 bucks, and I had some that he was paying 0.437 cents or something like that, because that 48 had to be used. It was in the problem, so some of them multiplied it and some of them divided by it, okay? And they both got ridiculous answers. I said, would you have paid this much if it was high, or do you think the store owner would let you buy 3 boxes of cookies at $1.19 for about 7 cents? I don't think so. Okay, you know. So you don't have to use all the data in the problem. There's no conservation of data. If that makes any sense. There is a checkpoint there, well worth your effort to do the checkpoint. Yuck, we're not going to have time for bearings. So we're going to begin next time trigonometry and bearings. All right, let me mark that. But we're within, well, there's a little bit more. We should finish the chapter next time. I hope we will. Homework exercises here. Do any of the odds 5 through 11. All 4 of those are at calcchat.com. 9 is at CalcView. Do any of the odds 13 to 15. No, either 13 or 15. They're both at CalcChat. 15's at CalcView. Do any of the odds 17 through, whoa, Looks like maybe through 31. Because the rest of those you get into the bearings. Okay? So let's just do 17 to 31, and we'll pick up the rest of those next time. Okay? And as I said before, if you haven't already, probably a pretty good idea to be working toward finishing that first test so that we can, I can get those graded and back to you. I think half of you have turned them in and half of you have approximately. All right. And have a good weekend. Remember, I will not be available in my office much this afternoon at all. I'll be there while I eat lunch, and then I'll be in the Ethel Hall building for the rest of the afternoon until I have to leave and go to Jasper. So, and then I'll be back here on Monday. Good deal. I may have let you go a few minutes. We were right on time, I think.